Hello everyone and welcome back to the Funtastic Academy with me, Ayush Prasad. Today we are going to learn about a brand new sorting algorithm, one that's very commonly used and faster than all the other sorts. You could say it's the quickest sort. Quicksort. Invented in the 50s by mathematician Tony Hoare, Quicksort is commonly used for its speed and effectiveness at sorting large arrays. Today, we are going to learn about how exactly Quicksort works. And in the next episode, we'll learn about how to analyze how fast it is. But before we continue, let's answer the quiz question that we had from last episode. How many layers of recursion does merge sort have? The answer is log of n. Merge sort takes log base 2n iterations of merging in order to fully sort the array. Without that out of the way, let's learn about the fast algorithm quite similar to merge sort. I'll pass the mic to computer Ayush to teach you the ins and outs of quicksort. Thanks for that, Ayush. Now it's me here, computer Ayush, ready to explain the quicksort sorting algorithm. Now, quicksort is quite similar to merge sort in that there are two functions. One is the high level, which calls other functions recursively, and the second layer function does most of the dirty work. In merge sort, that was the merge function. Here is the partition function. Now let's understand how quicksort works on a high level. We are going to sort the list between the low point and the high point. Now we check if low is different to high, and if that's true, then we choose an element called the pivot index, which is equal to the result of this partition function. This partition function does some sorting to the list and returns the pivot index. After that, you sort everything below the pivot index and everything above the pivot index. Now, what is this pivot index and what is partition? Well, partition chooses a random pivot element in the list. And what it does is that it brings that pivot element to the right place and it moves everything around the pivot to the right place. So everything that's smaller than the pivot comes before the pivot. Anything that's bigger than the pivot comes after the pivot. But still, those two halves, the smaller half and bigger half, are not sorted in and of themselves. So we need to sort those two halves, which is what these two function calls does. The partition function is the real heart of this algorithm. Now we keep doing these recursive quick sorts in each half until we're sorted. Now we don't usually do these quick sorts all the way down. This is just a demonstration. We use something better like insertion sort because quicksort can become slow for a small list. Quicksort is actually much faster than insertion sorts for the bigger lists, and today we're going to see how that happens. Now the mean to this algorithm is in the partition algorithm. Partition takes a list sublist from low and high, and the first thing it does is select a pivot. Now, you want your pivot to be somewhere in the middle of the list. If the pivot is bigger than every element or smaller than every element of the list, then everything falls to one side of the pivot when you do the partition, and therefore you don't get as effective sorting. Now, there are many different advanced ways of choosing to pivot. Here, we just choose the last element of the list, but there are better algorithms such as the median of 3 method, which you could look into. Over here, we partition the list around the pivot. There are many different partition schemes which allow you to do this. The one that we have here is called the Lomuto scheme. Lomuto is not that efficient. It requires more sorts and comparisons than necessary, but it's quite simple and beautiful to see, which is why we're using it. Now, we set I to be the first element of the list, and then we loop the value j between low and high minus 1. Since the high element is going to be the pivot, j goes to every element that isn't a pivot. What I've done in this example here you can see we have an exemplar of sorting the elements of a list of with 8 elements. We represent element I with an underline and element j with bold. So here we have the first iteration of this loop. The first example is just the initial state of the list. So in the second here, we have the first iteration of the for loop. Here we check if the jth element, the bold element, is less than the pivot. It's not less than the pivot. Our pivot is 5, the last element, and 6 is not less than 5. So we do not do anything for now. Then we go to the next element. We increment the bold counter, j, and we look at where it lands. Now currently it lands on 2, which is less than 5. So what do? We swap the ith element with the jth element, and we increment I. So the 2 swaps with the 6, and we move the underline towards one space. So now 2 and 6 swap, giving us 2, 6, and the underline is here. Now in the next situation, we go to 8. The boldness lands on 8. J goes to 8. 8 is bigger than 5, so we don't do anything. But after that, we go to 1, which is smaller than 5. So we swap 1 with the underlined element 6. 1 and 6 get swapped and we move the underline forward. And we keep doing this. 7 is bigger than 5, we don't do anything. But 4 is smaller. Swap 4 and 8 and move the underline forward. 3 is also smaller. Swap 3 and 6 and move the underline forward. And the last iteration, when j has gone to every element except the pivot, the final thing we do is swap the pivot back into the ith position, the underlined position. So as you can see, after this, the pivot 5 is in the right place, the 5th place. Everything under 5 is on one side and everything over 5 is on the other side, and we can sort each half neatly. Now, you might wonder, how does this algorithm work at all? Well, it's quite simple. See, at every point in this program, everything between the start of the list and just before I is less than the pivot. And everything between I and j is greater than the pivot. Obviously, this is true at the start when I and j are just starting out. And the idea is every iteration we have to maintain this, that under the underline is less than the pivot, after the underline is greater than the pivot. And we consume an element each iteration to make this the case. So let's say we encounter an element that is larger than the pivot, such as say 7. Then we don't do everything. It's already on the right side and we keep progressing. But here we encounter an element that's 4. It needs to be moved to before the underline. It's not on the correct side. What we do is we move 4 and 8 swapped. So now 4 is at the underline. Then we increment the underline. So now 4 is before the underline in the correct spot. And the 8 that we swapped, don't worry, we increment j as well. So j is now in the sorted subarray. So this is what we mean. Everything before and up to j is always sorted as we go to this program around the ith element. The ith element is the pivot. And this is why once we finished, we swap the pivot into I so that everything is around I, the pivot. Now, that's a simple explanation for how Quicksort works. And in the next video, hopefully we'll cover more about how to analyze the algorithm and more about its efficiency. I'll now pass to Ayush to give you a recap of what we learned. Thanks for that, Computer Ayush. Now, let's just recap what we learned today. We learned about how exactly Quicksort works. on a high level, partitioning the list around a central pivot. On the lower level, we learned how the Lomuto partition scheme works to accomplish this in a fast and effective manner. But before I end the episode, let me leave you with one quiz question. The Quicksort was originally developed by Hoare at Moscow State University. What problem did he have that required him to develop such a fast sorting algorithm? Tell me the answer, and I'll see you next time on the next episode of the Funtastic Academy. Bye!